Okay, so continuing off from where we left off, let's go over the programming basics of the language. First of all, as you know, the language is based off words. So in order to start a word, you type it in red, and to end it, you type it a semicolon in bright green, and inside, whatever you type, this will be part of the function. So let's say 1, 1, and then plus. The ones are numbers and the plus is a call, or it could also be a macro. I call the word by typing in bright green and press F5, and as you can see in the left part of the screen, this tag shows a 2. This brings me to the RPN nature of the language, that is reverse Polish notation, which puts the operators at the end and the parameters at the beginning of the execution order. By doing this, we avoid any complexity of mathematics. We don't have to use parentheses anymore because the order becomes implicit. So for example, let's say I add a 2 and then I multiply it. What will that result? That will be 1 plus 1 multiplied by 2. That will be 2 plus 2, 2 by 2, and that will be 4. Since the language is stack based, we need words to operate on the stack. We have quite a few, but not a lot, and they're all very simple. So let me type them here in the interpreter. So let's say I put a 1 on the stack and I type dupe. This will duplicate the top item of the stack. If I type drop, that will destroy the top item of the stack. If I type swap, this will swap the top 2 items of the stack. If I type over, this will bring the second item to the first as a copy. And if I type rot, this will bring the third item of the stack to the front. So we will have 1, 1, and the babe. There are also other words. There is nip, which will destroy the second item on the stack, and there's also 2 over, which will, for all intents and purposes, make a copy of the top 2 items of the stack, so you can manipulate them in a word. That will give us 1 and that babe, 1 and that babe. If I drop and then drop, we're back to where we were. Now that we're done with the stack words, we need to talk about the return stack. The return stack is the second stack of the language. One is for data and the return stack is to hold the return addresses, but you can also use it to hold data temporarily while you work in a word. So for example, let's say I put a 1 here, a number 1, and I use this word. The push word is written as greater than and capital R, and this will push that one into the return stack. If you end the word like that, it will crash because it will be returning to the address number 1, which is not allowed to be accessed in Linux. So in order to bring back the item on the stack, you do the reverse. You do the less than sign and the capital R, and that will put that one back on the stack. If I test this word by pressing F5, we'll get a 1 on the stack. If you don't want the item you pushed onto the return stack to return, you can just do a return drop, which is typed like this, capital R and a lowercase d, and that will get rid of the top item of the stack. So if I press F5, nothing should happen, and nothing has happened. Now you can use that return stack to access it as if it were a variable. In fact, we have 2 variables. We have the I and the n, which are the first 2 items of the return stack. So if I put a 7 and a 1 and I push those 2, and I put the I and the N and I add them. When I press, I should get an 8, which is what happens. And I drop the 2 items on the return stack. Something you have to have take into account when you are using the return stack is that all the words of the return stack have to be inlined as a macro. This is because the way they are defined, they have a semicolon. So if you call them as if they were a call, you will jump here, execute the word, and then you will return, but you will have the incorrect address on the return stack, so you will probably crash. So just to be safe, you have to macro all these words. Aside from that, we have the arithmetic words. It's just plus, minus, multiply, and divide. There's also the mod operator. They all work like you're used to, except minus and divide have order issues. For example, you have to have in mind that if it's read 12 minus 1 and divide is read the other way, it's just a way of convenience. So let's just do a test here. So 12 minus will be read as 12 minus 1. If I press F5, I get an 11. If I do it the other way, I'll get a negative number, which will be 1 minus 12. Same for division. So divide is done in reverse, so it will be read as 12 divided by 1. And this is because it's easier when you're programming. You don't have to go swapping arguments. So if I press F5, 12 divided by 1 is just 12. 1 divided by 12 is 0 because it will be floating point value, but we don't use this, it's just integer math. Other than that, there's multiply and there is plus, and there's also the mod symbol, which will do the remainder of the operation. So let's do 25 divided by 5 mod, and that's 0 because it divides evenly. 525 mod, that will be 5, which will be the remainder. Aside from that, there is also the binary operations, which are just like you would do them in C. There is 2 greater than, 2 lesser than, those are the shifts. And there are also fixed shifts, would be, for example, this is a shift to the right by 2, by 4, by 8. And if you want to do a larger shift or a shift that has no defined word, you use the shift operator and the pound symbol, plus you put the number you want to shift. So let's shift to the left 1, and that should be an 8. There are also the logical operators. Instead of typing them like this, you type them directly. So AND, OR, XOR, and NOT. There's also negate, and these are pretty self-explanatory. You use AND to AND two arguments together. Same with OR, XOR, NOT, and negate. It's just straightforward. Okay, now let's move on to memory. You can pretty much manipulate the entire memory space if the operating system allows you. Since I'm here in Linux, it probably won't let me read something that I'm not supposed to. It will do a segmentation fault. But if you were running on bare metal, that will be no problem at all. In order to read memory, you use the add word or read it as fetch. And in order to store memory, you use the bang, which we read as store. And there are various sizes. The add by itself, it will read the entire word, that is 4 bytes. If you put an H, it will read 2 bytes, and if you put a B, it will read 1 byte. Same with the store. Store H, that will be store half, it will store 2 bytes, and store B will store 1 byte. Now let's do some testing by allocating memory and reading and writing to it. So we define a word, and in typing in immediate mode we say the number we want to allocate and or allot. Alloc will leave the address on the stack for you to manipulate, and allot will just drop it, effectively making this something like a malloc, although you can call malloc in this language, but is usually not needed. So now that we have our memory allocated, I call the name of the word using the magenta color. If you see down in the status line, you can see that it says ref, and this will give me the address of that memory. If I press F5, I get an address on the top of the stack, and I can read from that address, which is just garbage, and I can also store to that address. So let's just say I store AA, BB, and CC and FF as a hex number. Remember, press F8 to convert the number to hex, and I will store that. If I press F5, I will get the address, because store doesn't drop the top item. So you can do store at and store and fetch back the number. So if I press F5, you can see I have stored into memory, and I have fetched that memory from the address space. If I want to fetch the lower part, I do an add half, and that will bring the CC and the FF, that's the lower word. If I read add byte, that will just be FF, which is just the lower byte of that memory. Now I have 32 bytes allocated, so I can increase the address, so that will be like manipulating a pointer. And instead of fetching the first item, the first 4 bytes, I will fetch the second 2 bytes, and that can be used, for example, to write incrementally, because we are using a stack language. We can do these things in sequence. So let's say the first word is AA, BB, CC, and FF, and the second word will be 1, 1, 2, 2, 3, 3, 4, 4. I will store, I will add 4, and I will store again. And with that, I will have stored these 2 values into memory, and I will get the address on top of the stack. So if I fetch, I should get a 4, 4 if I fetch a byte. And and of course I did it in the wrong way, so I wanted this to be like this, because remember, it's a stack-based language. So the first item that the operator will see is this FF, and the second item will be this 4, 4 address here. So if I press F5, now I should get the 4, 4 I told you, because I'm reading the second item, even though I typed it first back here. So this is pretty much how you store memory and read memory. Now before we go further, let's talk about the debugging capabilities of the language. If you type 2 pound signs, that will be your debugger. You press F5, and whenever this symbol is called, it will halt execution, so and show you the contents of the stack at that moment in time. So if I do another pound debugger here, I press F5, and that will show me the first breakpoint of sorts. If I type or press any key except escape, that will continue to the second breakpoint. And as you can see, the stack has updated, and you can see on top, you can see the registers So the top register has the top item of the stack. If I press escape, that will reset the machine and compile everything again and bring me to the editor. Okay, so now let's see if I do this and step like so. So first we will have the address of the memory we will store. We will break again and we will have the address, and let me just add 4, and finally we will store. So let's give it a try. So we have the address and the number. I press a key and that gets stored, and now we have the next number in line, and I'm back to where we were. That's pretty much it for debugging. You can also use if you look at the source of the pound debugger, you will see one behind. You will see that it has this bracket and question mark, and that will set the debugging screen, while the closing brackets and question sign will display the screen. So you can use this to your advantage. For example, you can do something like this. You begin the debugging and you want to display like a message, so you say debugging and you tag it as a data string, and you use the word .s to print the string, and you end the debugging session. And if I press F5, I should have the string printed on the screen, and as you can see, we have it. So this allows you to make your very own debugging words. Say you want to dump this memory here when you debugging. So let me just look at the source of dump and make a special debugger. Let's call it pound, and I will begin the debugging. I will get mem as a reference, and I will dump 4 lines, and that will be our debugging. So let's just test it. Let's see, sdebug and sdebug, and press F5. See if this doesn't crash. And now you can see that we have the address here and the contents of the debugging here, and text dump right here. If I press a key, you will see that the contents will have changed, but we won't see it here because this is already in memory. So let's just change it to like 66554433, and these two A B C D E F 0, and that's 1 2 3 and 0 0. Right, so let's see. I have stored the first one, and I will store the second one in the next debugging step, and I'm seeing the memory when it's happening. Now let's talk about registers. In PC32 we have 2 registers, the A and the B register. The A is used for reading and the B is used for storing. In order to store into those registers, you type store A or store B, but usually what we do is do A and open brackets and B and open brackets, and this will save the register in A and store it the new value, and same with B. And in order to come back, we close the brackets and A and type A, and this will restore the A register. This is because the A register and the B registers are used in compilation. The A register holds the source code and the B register holds the place where you will be compiling to. So you have to save them always, just to be sure. although while in editor mode you can modify them. So let's say I type like 15 and store A, and as you can see here in the register window, you can see A is now equal 15. If I say 7 store B, you can see that the B register is now equal to 7. Although you can really do that while you're compiling code, because it will crash. So instead use the bracket options. So let's do like a test. Let's say let me put mem. Well, first but I am all over the place here. First, let me just store some words into mem. So let's say a B, B, C, C, and D, D, 1, 1, 2, 2, 3, 3, 4, 4, mem store 4 plus store, and I get the memory here. If I press F5, I will get the memory on top of the stack, and I will store it into the A register. So if I put the debugger here and press F5, you can see it's not there, but it should be here in the A register. That memory should be there. So let me just drop it, because we have added an offset to the memory, and bring it back. Okay, so I set up the memory, and in the next line I will go over and start reading that memory. You can use quite a few words for that. You can say a at plus, which will read 1 byte, a at 2 plus, which will read 2 bytes or a half word, and a at 4 plus, which will read the 4 bytes or an entire word. So let's just do a at plus, a at plus, a at plus, and we will have 3 items on the stack. If I put the debugger, 3 debuggers in here, and press F5, I will get the first item. That's the first byte that I had stored, the second byte, and the third byte that we had. And when I end that sequence, I will do the close bracket A, and that will return the A register as it were, and continue execution. So we can see that we had the numbers just as they were before. Now we don't have to do this all the time we want to store memory. We can use the comma operator, which is just a shorthand for this a at plus and a at plus 2 and such, and so on and so forth. But for the B register we use the comma. So comma 1, that will be compile 1 byte, comma 2, that will be compile 2 bytes, and comma, that's a natural 4 byte compilation. So let's just give it a try here. Let's not store in memory when we are testing the word. Instead, let's just store it directly here. So we type the word in hex, and we make it immediate by pressing F3, and we do an immediate comma, and that will compile that 4 bytes into this area of space and increase the pointer to the next word. Then we can also compile let's say one byte at a time. So let's say I want to compile a 1, compile 1, compile 1, compile 1, compile 1, a 1, a 2, a 3, and a 4, and we will have stored a word of data. So let's see, if I read 1 byte, that will be 1. If I read the second byte, that will be 1, 2, and the 3 bytes, that will be 1, 2, 3. And as you can see, we have store memory before we begin compilation. No, before we begin interpretation. We have done that directly up here using the comma word. Of course, you can also compile while you are in a word, so it's just that flexible. For example, if you say a at plus and then comma 1, that will be effectively reading 1 byte and storing 1 byte. So let's say that you have destination. Let's see, destination 32 bytes a lot, and you have mem and destination in B. And here you restore A, which came first, and then B, and you can see, and let's do some more compilation. A at plus compile 1, and if I get destination and dump like four lines of the memory in destination and do a display, let's hopefully it won't crash. We get our display, and you can see here that it compiled 1, 2, 3, because we read 1 here and compile, read 1 and compile, read 1 and compile. Next, let's talk about loops. There's only 3 kinds of loops. Technically there's only one actual loop. There is the for next. This will start the count, and this is the actual loop. It will loop back to here. So let's say 10 for next, and I will call I, because this for will push this 10 into the return stack, and as if you remember, you can access the return stack by using the I word. So this will give you sort of like a counter, but it will go from high to low, so you have to keep that in mind. So let's just do a debugger and just drop it, just so we don't clutter the stack. So if I press F5, I will start counting. First I have 10, 9, 8, and if I want to get out of the loop, I just press escape. Right? So that's pretty much the basic loop. There's also the open bracket and while colon. This will execute while the top item of the stack is valid, and this will consume one item on the stack. So for example, if you say, let's say I have minus 10, right? Oh no, let's say I have 10. I keep the 10, I will duplicate it, and I will subtract 1 minus. I will duplicate it, and I will execute this. If I put my debugger here, press F5, you see that we will start going down, and when we are at 0, it will end execution and leave one item on the stack, so you will have to drop it like this, or you can also do D and semicolon, which is just shorthand for drop return. There's also the until loop, which will execute until the top item of the stack is valid, that is, it's greater than 0. So if I say minus 10, and I will duplicate it 1 plus, and I put my debugger and press F5, and of course it won't work, because we are duplicating the top item, then we are adding 1, and we're checking that 1, so it has to be in reverse. If I press F5 now, you can see that we will start counting up, and by the time we get to 1, the loop will end. Okay, so now I've done a little bit of cleanup, and let's talk about conditionals. So in PC32 there are just about 2 conditionals. There's if, and there is if 0. And there are some variations, such as if drop, which will drop the first item of the stack, and if 0 drop. This if and if 0 will start the conditional, and then the semicolon will resolve that conditional. This is the semicolon will be the standing for the word then, but I just have found that typing semicolon is just easy, and since we are using color to define test or to define the red words, we don't need to have the traditional semicolon word as in normal words. So there is that. So let's do a test. So let's say 1. If 1 is valid, that is greater than 0, we will duplicate it and add them together, and then continue here. So if I press F5, you will see that I'll have a 2. If I say -1, I will have a -1 on the stack because 1 is not valid. If I say if I say if 0 and press F5, you will see that we have a -2. The ifs don't consume the top item of the stack, as you have known. That is in order to not have to do tup if. Instead you have to do if drop, or you can just type if d, which will drop it automatically. So for example, let's say 1 1 0 equals, or let's say 1 7 equals. Let's duplicate that. That would be 1 1 7 equal. Let's see in our by pressing F5, and you can see that it's obviously not equal, but if I do 1 1 equal, well, it will be equal, it will pass the test and do the addition. So let's do something like this. 7 if 7 is equal to 7, then you will add them together, so we will have a 14. And if I look inside using the pound debugger, you can see that we only have a 7. If I get rid of the drop, you will see that we have a 1 and then a 7. And that's pretty much it for the if constructs, at least the basics. You can also have the word cont, which is just, it puts a 0 and a drop. So for example, if the condition passes, we will duplicate, then add them together. But if the condition doesn't pass, it will just continue as if nothing had happened. We get a 1 on top of the stack, and if the condition passes, we get, oh, I need the drop, we get the 14 on the top of the stack. Aside from that, there are other conditionals, such as the question mark, which is used to return immediately if the condition is not met. So for example, let's say we make a word called is it a 7, so we duplicate it, we check if it's a 7, and if it's a 7, we add 1 to the address, to the number, and we return. So 7 question mark as a call, it will give us an 8. If it's not a 7, it will just give us the number and continue execution just normally. So let's say we ask if it's a 7, and whether it's a 7 or it's not a 7, it will add 1. So we have a 2, and if it's a 7, we have an 8 plus 1, that will be a 9. Same as the question mark is the 0 question mark, so that means if it's not the if this condition doesn't pass, it will execute this. If it passes, it will just return. So let's say 7 question, and we should have a 3. If it's a 7, we should have an 8, right? And that's pretty much it for conditionals. You can also build your own, but by experimentation I've noticed that you really don't need anything more than these conditionals that I've shown you, the ifs and the question marks. Oh, I lied. There's actually one more conditional I almost forgot, is the case conditional. And well, it's case of, and you have to call them in a separate word. Let's say the case, and you call it like this. So 1 case of, 2 case of, 3 case of, and so on and so forth. If the number equals 1, you will execute something. If the number equals 2, you will execute something. And finally you type end case, which will drop the number. So let's do a test here. Let's say 1 the case, and put the debugger here, and let's put something. Okay, so 1 t case will execute the case for the number 1, and as you can see I'm putting an 8, and that will return using the off, which is just return then and then drop. So if I do 1 t case, that will be 8. If I do 2 t case, let's say that's 16, and 3, let's say it's 32, just for an explanation. Let's see, 2 t case, that's 16, 3 t case, that's 32. If you have a number and you don't know the default case, well, you have to continue here. You drop that number, and let's say that the default case is 4. If I put the debugger here, and let's say I put 16 t case, and let's see. Oh, I put the debugger before so that will be equal to the default case. Okay, so with this I think we're pretty much done with the basics. I know I said we will be programming, but the video is running a little bit too long, so let's just split it here and do some actual programming in the next video. I'm sorry. As always, leave a comment, subscribe, check out my Patreon, and I'll see you next. Bye.